Okay, this video is going to be kind of an expansion on the AVL tutorial that I posted. But in addition to that, it's going to go through an example in how all this is going to work. Okay. So an AVL tree is a self-balancing tree. We talked in lab yesterday, or we had a question in lab yesterday about why that's important. And we'll see an example toward the bottom here of why that is. Okay. So the AVL tree self-balancing, it was invented in 1962. This Addison, Velsky, and Landis, that's why it's called the AVL. Okay. It's important to remember that it is a not a standard, it is a binary search tree, okay? Which means that when we're done with an insertion, it will have the binary search tree property of all left children being less than and all right children being greater than, okay? So we're going to one of the questions yesterday was how can we avoid this problem of trees being unbalanced? And what we're going to do here is that we're going to, at every insertion, we're going to check to see if this has created an imbalance in the tree, and if so, we're going to do some rotations to fix that. Okay. We do that through this idea of a balance factor. Now, the balance factor is going to be added to the AVL tree node. So we're going to take the regular tree node that we had before, and we're going to add this one to it. Okay. When we add that one to it, then we're going to have a balance factor for every node. Okay. So the balance factor is going to be determined by taking the height of the left subtree and subtracting the height of the right subtree. Okay. So we're going to allow, and you have to allow, these to be off by one. So if we have the balance factor being zero, a positive one, or a negative one, okay, so then we're going to say the tree is balanced. Okay. And since we're doing left minus right, if it's the minus one, it's right heavy tree. If it's the plus one, it's a left heavy tree. Zero means it's perfectly balanced. Okay. If the balance factor becomes plus two or minus two, it's never going to be any greater than that because we were at balance before we add the new nodes. We're balancing at every node insert. Okay. So if it becomes unbalanced, a two or a negative two, we have to do a rotation. Okay. The rotations then are used to restore balance after we do an insert. Same thing when we do a delete. A delete can unbalance things. And there are basically four cases for the rotations. Okay. And if the case is we have a left, which means there's a node with a left child and a left child. Okay. And that's all we have. That's going to be a two on the left minus zero. So the balance factor is two. That's a problem. So we're going to rotate that, and we're going to see that this visually. We're going to rotate that to the right. Okay. So there was an insertion into the left subtree of a left child. If a right would be the insertion into the right subtree of a right child. Okay. And that would be things getting bigger, like if we insert one, two, three. So we have to rotate those to the left to balance them out. They're leaning right, we go left. Okay. And then sometimes we have, I guess I would call it like a dog leg, where you have the insertion, the right subtree of a left child or the left subtree of a right child. Okay. And both of those require two rotations, either a left right or a right left. The first one is to straighten it out by just reversing or swapping the two. That causes it not to be a binary search tree anymore. So you then have to rotate the other way to fix it. Okay. So here are the algorithms, and I will post this document as well. I think the other document may have the algorithms as well for the different rotations that we have. Okay. So let's do an example here. I think it'll make more sense. So we're starting here. We're going to insert the numbers 1 to 7 in order. So 1, then 2, then so forth. And then we're going to balance after every step. That's what an AVL tree does. Okay. So I mean, I think you can imagine that if we just do 1 through 7 sequentially, we're going to have all right children, and it's going to be the same search efficiency as a linear list. Okay, so let's do it this way instead. We insert a 1. The balance factor is only one node. Can't have a balance factor. It's 0 minus 0 if you really want to get pedantic about it. Okay, we insert a 2. 2 goes to the right of the 1. The balance factor at 1 is now the left height is 0 minus the right height of 1. It's negative 1. We're still going to call that balanced. Okay. Next step, we're going to insert a 3. 3 goes to the right here. Now we look at the balance factor at node 2. I don't have that on there, but 2 is where we're adding it. Okay. So let me add that to that because that should be there. So we start at the node we added 1. So at node 2, our balance factor is a -1. Okay. It's 0 to the left, 1 to the right. Okay. It's a -1, which is okay. But at node 1, we have to check there. We see that it's 0 minus 2 or -2. We now have a right child of a right child, basically, a right case, which means a left rotation. So I like to think visually a left rotation is to balance this out. If you grab the 2 and lift it up, then the 1's going to go to the left, 3's going to go to the right. That's exactly what we do. We've now rotated in this way. Again, it's a left rotation. 2 moves to the left, 1 moves to the left. Okay. This is now balanced. We look here, it's the height is 1 minus 1 or 0, so that's balanced. Okay. Going to insert the 4. Following the normal rules of the binary search tree, the 4 goes right here. Look at the balance here. At 3, we're going to have a 0 minus 1, which is -1. That's okay. Go up to 2. We have a 1 minus 2, minus 1, balanced. Still good. Okay. When we go to insert the 5, okay, the regular insertion is to put it here. Okay. So we now have to calculate the balance factor at node 4 is just going to be 0 minus 1 minus 1. So that's a -1. That's okay. But at 3, it's 0 minus 2. Okay. And the 0 minus 2 gives us the -2, which means that we're imbalanced. Okay. And we have to do something about it. Okay. So again, we're at a right issue. Okay. So the right issue means we have to do a left rotation. We're going to grab the 4, pull it up. 3 will go down to the left, and the 5 will go to the right. Okay. So we do that. Okay. We now have to check the balances. We look at node 4. We're at 0. We have one left and 1 right. At 2, we're 1 minus 2, which is -1. We're still okay. Okay. So no issues there. Now we go to insert the 6. Okay. Following our normal rules, the 6 is going to go here. Okay. We now look at the node. At node 5, we're okay. It's, 0 minus 1 and -1. At node 4, we're 1 minus 2, -1, we're okay. But at node 2, we're at 1 minus 1, 2, 3 for -2. So we're imbalanced at a right. Okay. And we're unbalanced here at node 2. Okay, so here's the point that we're at. So we have to make sure that this node, okay, the other things are just kind of have to fall out as they go. And this is probably the trickiest of the rotations in this particular example. Okay, so I know the 4 is going to go up there, the 2 is going to go there, the 1's going to go down below that. The question becomes what happens to the 3? Okay. And we'll take a look at what happens to the 3. Okay. So again, the 4 pulled up, the 2's down to there, the 1's down to there. We know that 4 is the new root. 3 has to go to the left of this new root. Okay. So we just insert that in. So you go there, you want to insert 3, you go here, there's the 3. Okay. So that's how that's going to happen to deal with the lost element there. Okay. So we take a look at the balance here at 5, we're at -1. Okay. We're at 4, we're at 0. So we're good. Okay. Our last insertion is a 7. Okay. Which gives us these balance factors. Okay. At 6, we're at -1. And I guess the first time we didn't check that because really, when you insert a new one, you're not ever going to be out of balance. It's going to be either a 1, -1, or 0. But I put it in here just for consistency. Okay. So then we go up to the 5, and we see that this is 0, height of the left, 2 minus the height of the right. So that's -2 total. Again, that's an unbalanced right. I'm going to grab the 6, pull it up with the 5 off to the side and 7 off to the other side, which gets us here to our final tree. Okay. So this is a binary search tree, but it's also an AVL tree in that we've self-balanced it. Okay. And it just happens in this case, because I picked it this way, that we have it's perfectly balanced. And at node 6, we're at a 0. And at node 4, we're also at a 0. So it's balanced. Okay. Let's compare this to a normal binary search tree, which would look like this. Okay. And then for the AVL tree, our search is going to be a big O of log n. This is a binary search, right? We're getting rid of half every time. Okay. And since n is 7 in this case, our worst case scenario is about 2.8. Okay. And we can see from our final graph that the comparisons we would need to make in the worst case, which is either a 7 or it's not found, there's one comparison there, there's two comparisons there, and there's three comparisons there. Okay. Compare that to the regular binary search tree. We could see that for 7, we would have to have 7 comparisons. Okay. So this performance gets even worse if you ramp up as n gets bigger. Okay. So I just got some numbers in here. So if we have 100, okay, our worst case scenario is 100 comparisons. If we just do a binary search tree, AVL tree, it's 7, round up. Okay. At 1,000, which the lab asks you to speculate on, 1,000, worst case scenario, if they're inserted sequentially, is going to be 1,000 comparisons, okay, compared to 10 comparisons if it's an AVL tree, okay. 10,000, we go 10,000 versus 14, let's say, and 100,000 or 100,000 versus 17, okay. So the more that you have, the more important it is that that um, you have a balanced tree for sure. Okay. One of the reasons we do binary search trees is to do a binary search. That's why they're called binary search trees. So if they're not balanced, we're not really doing the job. Okay. So this was an example. Now, what this example didn't do, okay, that I may do some in class, just is the idea of the left, right, and the right, left. Okay. And that's, I guess I can do a real quick example here while we're at it. So what you're typically going to get with one of those rotations. Okay, let me do something here. We'll force an example. Okay. It's where you're going to have something like, say we have a root node of, say, 10. Okay. And we have a right child there of, say, 20. Okay. Which has a left child of 15. Okay. So that's a valid tree because they're all bigger than the parent and that's smaller to the left. Okay. The balance factor for this is going to be equal to 0 on the left minus 2 on the right, which is equal to a -2. Okay. We're going to have to do a rotation. Okay. And the way that we rotate this, it's two-part. So part one, I like to refer to as straighten out the tree, even though it breaks the rules of a binary search tree. Okay. And we do this basically by, we're still going to have the 10. We're going to go ahead and straighten out the 15 here. And we're going to put the 20 there. Okay. We can now do, so part two is do a left rotate in this case. Okay, so we moved 15 to the right, so we're going to call this a right rotation. Gets us that. Then the left rotate is where we pull the 15 up as the root. Okay, with a left child, a right child, the 10 over there, and the 20 over there. Okay. The balance factor there is 1 minus 1 or 0 at node 15. So that's how we straighten those out. Okay. So hopefully you'll take a look at this before class tomorrow. We're going to be doing some on paper, and knowing this will make it go much quicker for you. Okay. So if you have any questions about this, just let me know. Text me. I'll be around tonight, most likely.